Fast. Okay, well, we're awfully quiet. So today, guys, 5C.3, I'll come check, see how we work with C1, C2. I would envisage today's lesson being dedicated to polishing off all of 5C, and hopefully then we can have some time to look at our folio. So I hope you went okay yesterday. My apologies, I wasn't here. Let's get straight into it. So we're revisiting kinematics, right? So we're problem solving with kinematics. This time we're using integration techniques. And we should remember from differentiation that displacement, it's position with regards to time. And if we differentiate displacement, well, the rate of change of displacement is velocity. Okay, when we differentiate a function, we get its rate of change. So velocity is the rate of change of displacement. And you differentiate velocity, you get acceleration. Acceleration is rate of change of velocity. So if that's how we go with differentiation, then obviously the reverse is true for integration. If we integrate the acceleration function, we get the velocity function, and if we integrate the velocity function, we get the displacement function. So we have a solar sail accelerates at, and we have an acceleration function here, a of t, it's equal to 100 on top of t plus 2 squared. Okay, in meters per second squared. Part A. Find v of t, given the initial velocity is 0 meters per second. So find the velocity function. So that means we're going to have to integrate this. Velocity is equal to the integral of acceleration. So if we integrate this function, we're integrating with regards to t, because t is our variable, so we're going dt instead of dx. Now the way we're going to treat this is we have ax plus b to the power of n. So there's a couple of properties of integrals we can do to simplify this. We can pull the 100 out the front, and we're going to express it as t plus 2 to the power of minus 2. Okay, so now we can see it's ax plus b to the power of n, and so we're going to integrate it using the formula of ax plus b to the power of n. I'll state that up here quickly. Okay, so we're just applying that formula there. The 100's going to stick out the front. So I have 1 on a, where a is my coefficient of the variable. My coefficient of t is 1, so I have 1 on a. And then we have ax plus b to the power of n plus 1. So minus 2 plus 1 is minus 1. And then on top of minus 2 plus 1, minus 1. Okay, now we have an indefinite integral. We don't have boundaries, which means we're going to put plus c on the end there. There is some constant for which this is true. Let's simplify this a little bit. So the whole thing is going to be negative because I've only got one negative. So I've got negative 100, and then at the bottom we're just going to have t plus 2. All right, I'm just going to take that straight to the bottom. Okay, plus c. Now, we need to find c exactly. We need to use the other piece of information we've got. This is the velocity function, but we've got this constant here. We're also told the initial velocity, so when time is 0, the velocity is 0. So we can write that up here. V of 0 equals minus 100 on top of 0 plus 2, so I'm substituting 0 in, plus c. V of 0 is equal to 0. When time is 0, the velocity function is equal to 0. And now we're just going to solve through for c. So we have a negative 100 on 2. We have negative 50 plus c. c is 50. So therefore the velocity function is minus 100 on t plus 2 plus 50. Okay. So that's part A. Okay, part B says, now that you've found the velocity functions, find the integral from 0 to 300 of the velocity function of v of t. So I'm just going to take our v of t and bring it up here. We have minus 100 on top of t plus 2 plus 50. And we're integrating the velocity function with regards to t. Now this is something that we could just whack in our calculator and evaluate it, but this is also something that we know how to do using integral calculus techniques, particularly since they've brought the integral of ax plus b to the power of -1 into the course. That's going to integrate to a log, isn't it? So let's evaluate this. So firstly, I'm going to treat this as minus 100. And then I'm going, what's the integral of 1 on top of t plus 2? All right, so it's the integral of 1 on ax plus b. All right, and that is 1 on a ln of ax plus b. Okay, so here we're going to have 1 on, again, a is the coefficient of t. All right, the coefficient of t is 1, 1 on 1. And then we have ln of t plus 2. All right, so that's what the first term evaluates to. I'll close this bracket there. And then integral of 50 is just going to be 50t, isn't it? And we're going from 0 to 300. All right, so let's start to evaluate these. We're going to have minus 100 ln of t plus 2 plus 50t from 0 to 300. Now let's sub in. Minus 100 ln of 302 plus 50 times 302. Okay, so that's when I sub in the 300. Then take away when we sub in the 0. We'll have minus 100 ln of 2. And then that, when we sub in 0 there, that goes to 0 anyway. All right, and there's not really anything we can do to simplify this, so let's evaluate it to 3 significant figures. We could bring the logarithms together and have that as an integer. It's just going to be a little bit messy, but if we want to answer in the context of the problem, right, we're talking about velocity. The integral of velocity is going to be displacement from point of origin. So again, rather than typing all of this in,
is that 302 or 350?
This one, 300. Yeah, good. Rather than typing all of this in, let's evaluate this statement. So just in your calculator mode, type in the function minus 100 on top of x plus 2 plus 50 at the end from 0 to 300. And we've got 14498. Now this is a great opportunity for me to talk about 3 significant figures when we have large numbers, because we've seen 3 significant figures when we're talking about decimals and so forth, okay? But 3 significant figures also applies to large numbers. So we want the first 3 non-zero numbers, so 9 rounds up, all right? So that means if the 9 rounds up, this is going to become a 5, and then these last 2 are zeros. Now we're going to need a unit for that. Well, we had acceleration was in meters per second squared. We integrate acceleration, we get velocity. So if our unit is meters per second squared, that means our distance and displacement is in terms of meters, and our time is in terms of seconds. It's all there in the question. We have meters, meters per second squared. So this answer here is going to be meters. What does it mean? Okay, the area, we can think about it in terms of area. Area under a velocity curve is always going to be displacement, okay? Occasionally it'll correlate with the distance. In this circumstance it will, provided it doesn't change direction. In this circumstance it does not change direction, which means it's the displacement and the distance, but you won't make an error if you say it's the displacement. It is 14,500 meters from where it began. The rocket, the sail, the solar sail has travelled 14,500 meters in 300 seconds. Okay, so there's a bit of context for it. So this exercise, we don't really learn anything new apart from taking our integration a bit further to include acceleration now. I think in the previous exercise, we were just looking at velocity and displacement. So, up to you.